change the gear a little bit, because I will talk about mainly theoretical work. But although there is a battery that you can build out of SYK model. Before I begin, I want to thank the organizers for giving me this opportunity. I want to begin by giving acknowledgements to my collaborators, Preetham and Dr. Anirban Datta. Preetham is a PhD student, and whatever I will be presenting is basically work done by him. So I will give a brief background on the Sachdevia-Kitai model. So it's an all-to-all interacting model between n Majorana fermions. The most important thing is it's strongly interacting and there is no momentum. The interaction terms, they are random, and they are Gaussian random variables. And here I have plotted two interactions, so I am considering 4 fermion interaction. So this model, as I just explained, it looks like this. These are Majorana fermion operators, and the J is the interaction, and it has 0 mean but a finite variance that goes like this. So this is a many body model, so I can do exact diagonalization. So if one does exact diagonalization, we can analyze the eigenvalue spectra, and the density of states shows exponential number of states just above the ground state. So that is the first signature of many body chaos. We can also be a little bit thorough. We can look at gap ratios, and the gap ratio shows the Wigner surmise distribution. And in particular, depending on n, you have Gaussian orthogonal, unitary or symplectic ensemble, and this Gaussian nature is the signature of many body chaos. Alternatively, we can look at spectral form factor, and there are 3 distinct regions here. So there is a region where this spectral form factor decays rapidly. So this part is non-universal, but here is where the thermalization happens, and just after this there is a ramp, and this ramp shows many body chaos with random that is explained by random matrix theory, and then we have a plateau. So these are finite n calculations. So what about large n? So in fact, I mean the original paper, so they look at the large n solution. So if you do a Feynman diagram perturbative expansion in the interaction strength, you will get all these Mellon diagrams, and when you sum them up, you will have the Swinger-Dyson equation, and this solution, this is exactly solvable. You will get a power law correlator, and this is a signature of non-Fermi liquid, but we are interested in chaotic behavior, so you can go ahead and compute the out of time order correlator. So this correlator is like, as the expression says, it looks at the expectation value of anti-commutator square. So in the beginning, if I am taking just local operators, so they will have a particular constant anti-commutator, but as time progresses, these operators will spread and this will change, and in a particular time scale, the anti-commutator will have this exponential growth, and this exponent is the Lyapunov exponent for the that shows the chaotic behavior. For the SYK model, this Lyapunov exponent saturates the bound. Okay, so so this is large n. So what about intermediate n? We don't have access to those results because the model is all to all. It's a little bit complicated to solve on a computer. So one option is we can try to look at a model that has fast scrambling, so that the scrambling time goes as log n. So this is what is like signature of fast scrambling, and but the model has to have order n interaction term and not like n to the power 4. So this is what exactly these authors did. They looked at the Sachdevia-Kitai model on a hypergraph. So this is a complete hypergraph, so it's all to all connected, and this is the original SYK model. So the number of hyper edges here goes as n to the power 4. So hyper edges are the number of interaction term. So what we can do is we can prune this model so that we keep deleting hyper edges. So we end up with a regular random hypergraph with very less number of hyper edges, so that the number of hyper edges are kn. So these authors, they actually show that this is an expander graph, and the expander graphs, unlike the lattice, like the usual lattice, the expander graphs, they have different number of nearest neighbors. So scrambling happens differently compared to the usual lattice. And they show that this model still can do fast scrambling even if it has order n interaction term. So the exact model that I am working with is this one. Okay, so this is the SYK model, but there is this extra XIJKL sitting in front, and this is actually 0 or 1 depending on this probability. So if it is, it's with probability p it is present, or with 1 minus p it is absent. So what it does is it modifies this variance. There is a correction of p in the denominator, and so the Mellon diagrams that I showed one slide back, the first order Mellon diagram has the same contribution to action, but if we look at higher order Mellon diagrams, there will be 1 over n and 1 over k corrections to action. So this will lead to fluctuation, but these authors show that even with this fluctuation you still can get the SYK physics. But particularly for this hypergraph degree greater than a particular minimum value. And these are some loose bounds they give. So the degree of this hypergraph is related to the probability through this relation. So if there is this k minimum, there is a PC or critical sparseness parameter present, above which you have a you see this SYK like behavior. Below that you don't see the chaotic behavior. So I will also look at this model. This is a spin xy sparse SYK model. So it looks like the same model, but the operators, they are not fermions. That's the difference. These are local operators. These are spin operators. So if you are familiar with Jordan-Wigner transformation, so I have just replaced the sigma j operators in the Jordan-Wigner transformation with identity. So not really I have, but these people who propose the model. So this eta ijkl counts how many operators are anti-commutating, because these sigma x, sigma y here, they will anti-commute. So you have to keep track of that so that the model is Hermitian. So for p equal to 1, this paper shows that you have a Gaussian density of states, which is the signature of the chaos behavior in SYK. But there are actually small deviation at the edge spectrum. At the edge of this density of states plot. So if we do exact diagonalization analysis, we also see that we can see that the level statistics, spectral form factor, all of this shows chaotic behavior, but these are finite n calculations. Okay, so they are also worried about, so because we are looking at spin half. And it has been shown that for small spins you can end up with a spin glass phase. So they look at the Edward-Anderson parameter, which indicates whether you have a spin glass phase or not. So if this parameter is 0, we don't have a spin glass phase, but if it is non-zero, which is the case here, they find a small non-zero value, and importantly it increases with ns. So later these people, they also look at the same model to do a more thorough analysis, and they find that some of the low energy modes can be in the spin glass phase, but there are also other modes that are SYK like. So maybe in some energy window it can give you SYK behavior. So why I am looking at this model is that my motivation is there has been many work to propose experimental platforms to realize this SYK model in like experimentally, so that we can simulate gravity in lab. So one of the key criteria is it has to be strong interacting platform with no single body term, random all-to-all coupling. So there are some proposals which, for example, uses flat bands in solids. So these are some notable papers. There is also some papers that suggest or proposes simulating an optical lattice and ultra cold gases. But what is more like motivation behind this work is that recent works, they have simulated SYK model in a quantum computer. So for example, there was a paper in 2022, they claim that they have simulated a traversable wormhole, and there is also in a recent paper they look at how to like algorithm to do SYK dynamics. So for all of this we have to actually understand how sparse the model can be, because sparse SYK model is very important or plays a key role in this quantum simulation. So and particularly the qubit one, that is important because the current platforms are based on qubits. So we have to understand in details whether what happens as the sparseness decreases. So these are some recent works. So for example, this one looks at the onset of this ramp time, and they actually suggest two transition probability, and here they look at entanglement entropy growth as a function of this sparseness parameter. This is some work on how Krylov complexity changes. So but here I want to we want to study a quantity called as stabilizer Renyi entropy. So this is a measure of quantum resource, mainly because there are other works, but no work has been done on this, and maybe it can also give some extra information. And also we want to compare, when we wanted to compare this fermionic sparse SYK with this spin XY sparse SYK model. And possibly we can write a traversable wormhole ground state if we couple these two spin XY sparse SYK model. So with this objective, let me tell you what is stabilizer Renyi entropy. So what is actual non-stabilizerness? So if I want to prepare a quantum state, I have to estimate the quantum resources required. So these are some examples: entanglement entropy, stabilizer Renyi entropy, robustness of mass. These are some quantum resources. This in particular that I am interested in, it measures distance of a quantum state to a stabilizer state. So a stabilizer state actually can be simulated in a classical computer in polynomial time, unlike the state that has non-zero SRE. So in that sense, state that has non-zero SRE might be difficult, but it also is also useful for quantum computation perspective. So the working definition that I will be using is this, and so a few points, because this is a formula, but alpha is the Renyi index, D is the Hilbert space dimension, and P here is the Pauli string operators. So what we are doing, or what one has to do, is sum over all these expectation value to the power 2 alpha. So these are the expectation value of all possible Pauli string operators you can write for n qubits. Okay, so a related thing we can look at is Pauli spectrum. So it's a probability density function for all the expectation values. Now this, so this entropy, for example, can be thought of as a participation entropy of density of states in the Pauli operator basis. So an example, so for example, this state, it has zero entanglement entropy, but it has non-zero SRE. Why? Because it's not an eigenstate of a Pauli operator. Okay, so this is a single qubit state. You can think of like making multi-qubit states where you have zero entanglement entropy but non-zero SRE. So the key challenge in computing this is that we have to compute 4 to the power n expectation values for 2n Majorana fermions, but there are already some papers that suggest that we can use a sampling scheme to do this. So before I go to the SYK results, because SYK has similarity with the random matrix theory, so I will just first tell a little bit about what SRE we expect for random matrix results. So for typical states, we expect that there is a Gaussian Pauli spectrum where the variance will be determined by these qubits. but also the Pauli spectrum will have delta functions corresponding to x values 0 and 1. From the Pauli spectrum you can calculate this SRE or the stabilizer Renyi entropy, and it has a scaling relation like this, where n is the number of qubits. So this d alpha is the magic density, but d alpha is universal for all Gaussian states, and c alpha is a subleading constant. So, so this kind of universal scaling is very important when we are looking at the Hamiltonian and we are trying to see whether we are close, we are seeing random matrix results. So the ground state stabilizer Renyi entropy results are like this, or some of this work are here. We are just comparing these two models. So as a function of number of qubits, if you plot, it shows the linear behavior, and one can see that the slope here is very close to 1. The slope of the model compared to the random matrix relation is very similar. The Pauli spectrum also we determine it to be this, where there is a Gaussian part and also there are some delta functions, and these we can understand what are these because we are looking at a particular parity, we are looking at a fermionic problem. So these states, the ground state has a particular parity and identity operator. So these two operators will give you this kind of delta functions in the spectrum. So all of this matches with the random state results or hard random results, but this is the dense model. So what happens when we add this sparsity? So as a function of sparseness, the stabilizer Renyi entropy actually goes down and it goes up, but already at this sparseness, the hypergraph, if you remember this hypergraph that I showed, it has already been split into subgraphs. So so actually the transition already happens somewhere here where the SRE is decreasing. But to understand this, we can look at the Pauli spectrum. So when we look at the Pauli spectrum, this is Gaussian, this is the dense state, but as we go away from this p equal to 1, I see that it is deviating from Gaussian. So this tail is getting fatter, or I mean, yeah, around the tail, but in the middle of the spectrum it is still Gaussian. So around here, around p equal to 0.008, there is a huge change in this Pauli spectrum. So how do we capture this? How do we get transition from this kind of probability density function? There is a standard technique. So if you want to compare two probability density function, there is Kullback-Leibler divergence. So one can do that, and then you see a peak somewhere, and that will indicate your transition. But this is very, I mean, it's expensive. So what we do is we look at where SRE changes maximally. So from that, we found this transition value, and this actually very nicely follows this fitting function. So why do we expect this fitting function, or why am I fitting it with this? Because if I look at the relation between degree of hypergraph and probability, so for a hypergraph, for a particular value of k which is independent of n, we will see a transition. So that means that the PC should behave like this when at the transition point. Okay, so so if I cross one of these, let's so I have taken n equal to 18, yeah, n equal to 18. So if I cross this, so I am if I look at 0.012 and 0.08, we see that the label statistics also agrees with what we are seeing. So it goes from a Gaussian to a non-Gaussian. So I will go ahead and look at discuss about time evolution of the stabilizer Renyi entropy. So I start with an initial state. I will do a quench evaluation with these two kind of sparse Hamiltonian I have. So at late times we expect that I will see this random matrix theory universality where the system thermalizes. For very low value of sparseness, it actually does not thermalize, but that is because I am above this PC. So below the PC, the entanglement entropy thermalizes, and also we see the same behavior for the stabilizer Renyi entropy. So if I compare the two models, interestingly, although the ground state, I can't really distinguish that much between these two models, but this evolution actually shows a distinction. So one of them, the spin XY SYK model, thermalizes slightly slower compared to the fermion based model. And so I mean, the thing and the important thing is that actually this difference actually grows with n. So one has to, and also the rate of that SRE grow or the difference in SRE also depends on the initial state. So so this actually raises the question whether we are seeing this because of the spin glass phase in the spin XY SYK model. So more analysis has to be done. This is just the SRE. So with this, I will conclude my talk. I discussed how the stabilizer Renyi entropy and Pauli spectrum changes as the sparseness parameter like decreases or out of the chaotic phase. And the two model, I compared ground state and the dynamics of these two models, and this is an ongoing work, and so we are working on writing a traversable wormhole ground state and seeing whether that whether the traversable wormhole becomes the ground state for the coupled spin XY sparse SYK model. And yeah, with this I'll take it. Thank you for listening.
Thank you for finishing a little bit before time. Are there any questions?
Thank you for the talk, ma'am. In the previous slide, you said that there was some initial state dependence of your system, like the thermalization.
Yes.
So, in which sort of states would you think that this is going to thermalize, let's say, faster or slower? Like, how can we differentiate?
We had checked a few states. For example, I start with 0000 state here in this plot, but if you do 1010, then you don't see any difference in the thermalization, and also some other states. Yeah.
But the rate changes, does it?
No, the rate. So the rate here you see a different rate for the two model, but for the some other initial state you don't see a difference, and for some other you see more difference.
There's no clear like pattern to it, let's say.
No, but one thing is that they all thermalize. It's not like for one state they are not thermalizing, and for other state they are thermalizing.
Thank you.
Thank you for nice talk. I was asking that the Hamiltonian which you have shown, so can we create, have you created randomness in that?
Yes. Sorry, you mean like the Hamiltonian that I wrote, I exactly used that? Yeah, this one?
Yeah. So how randomness is appearing here? Because in general, like we used to create randomness in the system, I mean Hamiltonian, and when we are, let us say, diagonalizing that, and it will take the level spacing distribution, LSD, and if we are able to see, I mean, so can we look like that here also?
So the reason I wrote random here also, here is this JIJKL, they are from the random Gaussian distribution. So that is the random, but here also there is another variable that is random, which is XIJKL, but it is just a binary distribution. So it is either 0 or 1.
Okay, so this single precision, like or double precision, will hamper the results or no?
Okay, I am not sure. What is single precision?
I mean, in general, people used to create this random number in the, let us say, Hamiltonian, and after then, if we are introducing like single precision random number and double precision random number, so sometimes it used to affect our results. So I was asking in that way. Maybe we can discuss later also.
Okay, I don't think it will matter as long as it is Gaussian distribution.
Okay, thank you.
usefulness of using Rene entropy as opposed to other measures of
So the one that I discussed, although I don't know the details, but there is a paper that says that it can be measured, the SRE, particularly in the quantum circuits where you can, I think you can count how many T gates. But for the entanglement entropy, like measuring entanglement entropy is difficult, but rather you can measure Rene entropy. That is because you can use a swap process that is not there in the entanglement entropy. I do not know the details, but there is a swap process that is used for measuring the Rene entropy, Rene entanglement entropy.
more suitable as a
Yeah, that makes it measurable, unlike entanglement entropy.
Are there any other questions? If not, then let's thank Mishra for this nice talk. The next talk is